I'm Anthony Brown, and I'll be chairing this session. And we'll be hearing much more about this business of using accelerations or proper motion differences to look for companions around stars. And first up is Brandt, who did a PhD on the topic, and he will tell us all about the results that Tim promised us yesterday. So go ahead.
I think I need that. Oh, thanks. Thank you, Anthony, for the introduction, and thank you to the organizers for putting this together and inviting me to speak. I would say the nice thing about having really good speakers come before you is that you have less to talk about, so you have less to mess up. So that's been really nice to see. So for instance, Jackie's amazing talk introducing brown dwarfs has saved me a whole bunch to say because I can't say any better than she can. And that's what I'll be telling you about is trying to constrain the properties of brown dwarfs and some giant planets, again, depending on your definition of what is a planet and what is a brown dwarf, but constraining their properties by combining Gaia and direct imaging. And I'll actually be talking not so much about proper motion anomalies because that's been covered in great detail, but what we might be able to do with Gaia DR4 and kind of the techniques involved there and the nuances, and again, aim towards kind of new graduate students that are just entering this and to kind of wrap your head around it and appreciate the difficulty and also the subtleties of doing this. So I'll start with the importance of brown dwarfs, and it'll be very brief because again, Jackie already talked about it and it was great. I'll introduce some of the tools to derive masses, some of which you've already kind of played with, for instance, in the hands-on session. I'll talk about these 1D measurements from Gaia, which for me personally were very confusing at first when I was first starting as a grad student. So I have some visualizations that hopefully will kind of clarify this. And then I'll talk about how you actually fit orbits and masses in the context of those 1D measurements and how this ties back into how direct imaging can actually help you fit those masses from those astrometric measurements. So just to kind of start off, this is everything I'm going to talk about here is based on work by many, many researchers. So I've listed some names up there of people at UCSB and beyond in our kind of greater collaborative group, but there are also tons of people who are not in direct collaboration with us that do work on brown dwarfs, giant planets, Gaia Hipparcos proper motion anomalies. Those names have been mentioned here. The person speaking after me is involved in this in great detail. So it's not just our little group. It's a huge a huge whole community, and we all benefit from the work that everyone else does. So again, I study brown dwarfs. I kind of laser focus on brown dwarfs. The spiel I like to give is that they lie in this intermediate mass range. And because of that, they can form both like planets or form like stars. So they kind of bridge the gap in understanding between star and planet formation. It's almost like killing two birds with one stone, because if you learn about brown dwarfs, you can also learn about how planets form and about how stars form or may form. So they're a really interesting thing to study, and they have the unique advantage that they're easier to direct image because they're so heavy, they're so big, and they're usually on far orbits from their star. And in this study of brown dwarfs, the mass is key. So Jackie talked about this at great length, but you really need the mass to not only understand the brown dwarf, but actually test models of their evolution. So if you have an independently measured mass, and by independent, I mean a dynamical mass, so something from Newtonian dynamics of the system, not a fit to a cooling model, you can actually begin to test these cooling models. So you can ask questions like, if you have a luminosity and a mass, you can ask questions like, how old this companion is, and actually start to ask the question of, okay, how might this companion actually have formed, and which models might it match? So I'll go into some results that answer those questions and kind of explore them and see and kind of push the limits of what observational techniques we have right now. So the first thing I'll talk about is HR 8799, and Jackie kind of teased us a little bit of talking about how we measured the first dynamical mass in the system, which is the mass of the innermost planet. And again, this was done by using Gaia and Hipparcos accelerations and direct imaging. And the nice thing about this study is that what we did was really, really simple. We didn't do any orbital fittings. There was no orvara or orbitize or anything involved in this. What we did is we used the orbits fit by Jason Wang et al. So we used the previous work's orbits because they did a really nice characterization of the orbits of the system. So we had the orbit of the planets in the plane of the sky around the central star. And as Beth mentioned, if you have that, you have the same major axis and you have the total mass, but you don't know anything about the masses of the individual components. But the nice thing here is that if you have an astrometric reflex motion of the star, so from Gaia, you have an actual motion of the star in the plane of the sky, then you can unlock the individual masses if you have the total system mass, which we have. And so HR8799 previously in Gaia DR2, if you looked at the significance of the acceleration, it was not a very good measurement. So in the old version of the Hipparcos Gaia catalog of accelerations, it's like a 1 or 2 sigma accelerator. So you could do this measurement, but the mass you would have found for the inner planet would have been 10 Jupiters plus or minus 20 Jupiters. It would have been not very well constraining at all. But in DR3, they improved the bright star treatment so much that this tipped over into a 5 sigma measurement, and we could actually get a mass constraint on this inner planet just by coupling the visual orbit that we didn't even do that someone else did. So by building on that with the astrometric motion. And I'll kind of detail that in a little bit. But because we have the mass, we can do this. We can actually calculate a dynamical or an age inferred from that mass by coupling this with cooling models. So I've shown here this probability density of the age of HR8799E based on its dynamical mass. And the orange and blue vertical kind of representations of Gaussians are the two supposed associations that this could have come from. And so right now, the age measurement is not precise enough to determine which it belongs to, just that it's commensurate with both of those at this point. It's a weak age measurement, but it's there. I mean, it doesn't give us something that says it's a giga-year old and something is totally way off. But future astrometry and better astrometry in the system is going to really tighten this distribution up and potentially tell us which association this system actually formed in and actually came from. So again, you can learn something about the formation history by doing these really careful dynamical mass measurements. So following on Tim's shameless plug of our own software, this work was a combination of htof, which is something we wrote in-house at UCSB, with another code called Rebound. Rebound is a great code. Go and use it. And this allows us to actually simulate the Gaia and Hipparcos measurements in a kind of kosher way to get at this MASH measurement. So htof really handles all things absolute astrometry. It really is aimed towards new graduate students that want to get started with absolute astrometry, but don't want to implement their own, sky path fitting routines, don't want to implement their own file reading in and out of all the intermediate astrometric data files. So when I say intermediate astrometric data, I'm referring to the raw positions on sky from Hipparcos, and also the scanning law from Gaia to give you a placeholder for that. So this is not a problem that's super difficult per se, but there's a lot of infrastructure that you have to build up around it where things can go wrong. And so htof has just done all the infrastructure for you. So you can fit a sky path in 1 or 2 lines of code and read in all these files and don't even need to think about it. And so this is the code we used with Rebound to actually do that HR8799 measurement. And Orvara is kind of the flagship of this open source software framework that we're trying to develop at UCSB to measure masses and orbits of giant planets and brown dwarfs. So Orvara is an actual, MCMC orbit fitting software, which you play with in the hands-on session, and htof is packaged inside of there. It's not actually, the code itself is not actually bundled inside the software, it's just a dependency. But the nice thing is that it means htof doesn't have to know anything about Hipparcos or Gaia intermediate astrometric data, file in and out, or anything, or fitting sky paths. That's just in there from another dependency. It's totally segmented and separately supported. So we talked about HR799E, and we talked about how we got an age from it. We got a mass. It's cool, and you can kind of maybe start to tease out maybe which associations it comes from. So a little bit about formation history, but it's not as detailed as we like to go. And so I wanted to talk about a study that Yiting Li and Minghan Chen did, and Yiting talked about it a bit in her poster pop. But it was a really nice study of epsilon Indy BA and BB. So this is a binary brown dwarf pair. You can see the BA component there is the bright component, and the BB component is the faint component. The cool thing about the system is that It's a binary brown dwarf pair. So we know it has to have the exact, both components have to have the exact same age. Because they have the same age, if we can get a really tight dynamical mass constraint on both and a really good luminosity measurement from a beautiful treatment of the relative astrometry, then we can do something more than just, okay, this thing is this X number of years old. We can actually make an isochrone of these two brown dwarfs. So you've looked at these beautiful fits of isolated stellar populations fitting to one single isochrone, and it's awesome to see that. But we can't really do that with brown dwarfs and giant planets because we don't have this really nice dynamical mass constraints for coevality. So this is an old system. There's been lots of work leading up to this work by Yiting and Menghan. But the culmination of it was kind of a recalibration and a readdressing of this beautiful set of relative astrometry and absolute astrometry to combine to get these nice masses. And so I think this is like the coolest thing of all time, to actually put these on an isochrone. So what I've shown here is a plot from their paper. So the two panels are identical in the sense that they're both isochrones. On the left are isochrones, so fixed age, differing mass, from a model called ATMO 2020, which is some treatment of brown dwarfs. The specifics aren't really that detailed for this point for this talk. And on the right are isochrones from a model from someone in Marley 2008. So you say, okay, big whoop, you can you can plot these brown dwarfs on here. So what is it actually telling us? Well, if you look closely on the left, this actually predicts that epsilon NEBB is a different age than epsilon NEBA. And this is a cloudless model. And it does not match the data for these two brown dwarfs. So this isn't saying anything about brown dwarfs in general, but for these two brown dwarfs, it seems like this cloudless model is not the way to go. But for SMO8, what's really interesting here is that these brown dwarfs are sitting on a transition, and one is supposed to be cloudy, and one is supposed to be cloudless. So the T dwarf that is cooled is supposed to be cloudless. And this is a really nice fit to the data. So these two actually lie in the same isochrone. So it satisfies this underlying constraint of coevality that we know must exist. And so now we're not only saying, okay, look, we've plotted these and compared them to models. We're actually learning something about their formation history. We're learning about, okay, in the LT transition, there's a slowed cooling, and there's accelerated cooling after it becomes cloudless. So you're actually learning something about the brown dwarfs and stepping into this regime where we're starting to test models of formation and not just build up a sample size that we can do something with at a later date. So I think this is super cool. Yeah, it's exciting. And again, the common denominator of both these examples is that we're combining relative astrometry and absolute astrometry. So there's no RVs involved at all. Pierre Crivello will talk about combining RVs in the next talk. I'm going to restrict myself to just absolute astrometry and relative astrometry, but you can combine RVs in here to improve things. So masses give us so much. I mean, I just give you two examples, but there's a beautiful flurry of papers out there that show what you can do with masses. They give us so much, but we have so few of them. So these are kind of order of magnitude numbers. There are about 100 brown dwarfs. So again, this is defined here as bigger than 13 mJ. Arbitrary definition, but that's just what I've done here. But in terms of image brown dwarfs with a known dynamical mass, it's roughly 20, so order of magnitude. And actually looking at all the posters out there, it seems like that number is probably going to double or triple because there are lots of newly discovered companions out there that you all have been working on. So it's nice that we are building up that sample. But again, it's not many. So we need to build up the sample size. And it looks like people are making a strong headway into actually doing that. Okay, so we need more masses. Obviously, combining relative and absolute astrometry is a great way to do it. The standard so far has been to use proper motion anomalies because it's really kind of the only thing we have. One of the problems is that if you use proper motion anomalies, it can average over short period orbits, so 1 to 5 years. So Tim sort of addressed this, that the proper motion anomaly method is best for things with twiddle greater than 5-year periods. So we have proper motion anomalies, but with Gaia DR4, we're actually going to get these individual position measurements for these systems. And that opens up a whole new realm of things that we can do. So again, we're combining relative motion, and I'm also contractually obligated to show this movie. Everyone has to. with absolute motion across the sky. So this is HR 8799. The thing on the right is not HR 8799, it's Barnard's star, but it's a very high proper motion source. So you can actually see it with your naked eye over 10 years moving across the sky. So you can combine relative motion with absolute motion of the host star to get the mass and the other orbital elements. So if you looked at this, you have Barnard's star there moving. Pictorially, or on a plot, you'd have, position measurements with some finite uncertainty. For instance, this is sort of what you get from Gaia. I'll go into detail of what you actually get, but let's just imagine that's what you get, is position measurements as a function of RA and DAC and time. Now let's imagine a fictitious heavy companion around Barnard's star. This is greatly exaggerated. The companion mass is greatly exaggerated here just to make this effect really clear. But what you would see is that the star is not following a straight path, but it's following some curved motion. And parallax here has been removed. So parallax makes stars follow a perceived curved path, but that's been removed here. You're just seeing the bend from the companion. So what's going on here? So you have the star and the planet both orbiting the mutual center of mass. And again, this planet mass is huge. This is like 150 Jupiter mass planet. But again, to make this effect large. But in the Earth's frame of reference, it's moving to the right with some proper motion. So it's tracing out this curved path. And the magnitude of that curved path is going to depend on the planet. And that's the mass of the planet. And that's what this method will rely on. And again, we can't see the planet, so all you just see is this curved path. So how do we solve for the mass? And I'll preface this by saying this is basically exactly what we did with HR 8799. So this should appear to you as being, wow, this is really simple. Like, this is super simple, because it is. And this is exactly what we did with HR 8799. So if you have direct imaging over a long baseline, you have the orbits you have the good constraints in the orbits. You know the eccentricity, you know the inclination, you know the same major axis. You know the total mass. You just don't know the individual component masses. But we can combine all that beautiful information with that astrometric path you just saw in the sky to get the mass basically linearly. It's super easy. I mean, if you have a fixed period, a fixed E, just scale the model motion basically until it fits the observation. And yeah, it's like super simple. That's basically what we did, except we were using proper motion anomalies, but the same concept kind of applies. I mean, that's it. You just back out the mass. So this is when we actually have these individual position measurements from DR4. For the sources where DR4 overlaps with direct imaging candidates, this is going to be incredibly powerful because it becomes quote unquote easy. I'll get into some of the complications, but it becomes quote unquote easy to do this. So I think this equation kind of summarizes everything of all the combining measurements. So the parallax, that var pi over there, comes from the Gaia catalog. The total mass there comes from direct imaging, and the same major axis comes from direct imaging. We don't know the planet mass. And when we have Gaia DR4, we're going to have that astrometric semi-amplitude, that path across the sky. And so effectively, you can just solve this equation for the planet mass. This is simplification, but that's basically what's going on. And indeed, for a face-on circular orbit, that would be the case, that you could just solve directly for the planet mass. How are we doing for time, by the way? Oh, sweet. Okay, cool. Okay, now the complications. So using the on-sky predictions can be tricky. I'm saying can be because I'm not going to make some broad swath statement that it applies to every source or it applies to some sources. I just want you to be aware of the interesting nuances that can come up when you're using the actual on-sky positions that will come from Gaia or those that are in Hipparcos. But Gaia is more relevant for this because its precision is so much higher. So these 2D measurements I showed, they're not exactly like the real Gaia observations. And I'll get into what they actually are. So before I do that, I just want to motivate kind of why this is tricky. And this slide isn't really per se needed anymore because Alessandro already addressed that there are places where things can be improved with the current binary solutions. So this is just a complementary example of that like, look, this is kind of a hard problem to do right. It's kind of hard to get exactly perfect. Not that perfect is the goal. And being perfect shouldn't be the goal because if it was perfect, then there'd be no work for any of us in this room. So it's actually a good thing to be, to have work that needs to be done. So for some systems, based off of this work that us and all these other wonderful groups have done, there are some massive companion orbits that we know so well that we can predict what Gaia DR3 should, if this was easy, have reported for the accelerations. So we just do that. We take these companion orbits, we fit the acceleration terms that if everything was perfect, what Gaia would have reported, and we can compare it. So I'm showing two example systems here from a paper in prep by Sharon et al. So she's in our group. So keep your eye out for this paper. On the left is the DR3 reported acceleration in RA. I'm just showing RA here. And in the middle is the prediction from what the known orbit is. And on the right is the actual Gaussian sigma discrepancy. And so this is cherry picking the worst of the example, just to show for some cases this can be hard. And so obviously, a 14 sigma discrepancy, there's going to be some interesting science lying in there of how to actually resolve that. And there are a lot of assumptions that go into this. So, if you want to ask a question about that, that would be great at the end. So I'm happy to talk about this more. So again, part of this, there's interesting science lying in resolving those discrepancies. There's going to be interesting things to learn about planets. Some of this comes from complications with the real, the actual Gaia and Hipparcos measurements. And so that's what I want to pivot to now, is kind of developing some intuition, especially for these, the new graduate students in the room who are just starting to touch these measurements, and those who will end up actually working with the DR4 measurements, come 25, 26. The first complication is that the measurements are not 2D, they're one-dimensional. So I'm going to explain what that really means. For that, we're going to do a simple example. We have some sky path with proper motion and an orbital motion from an unseen companion. There's no parallax. The companion mass is going to be huge again. It's like 150 Jupiters, but there's no parallax here. It's just motion across the sky with a companion. So in the case of 2D measurements, which would be the perfect case, right? At every one of these crosses, we have a time and an RA and a deck with some uncertainty. And the white is the actual underlying orbit these are drawn from. These measurements are drawn from. So recovering the best fit orbit in this case would be pretty easy. You have a nice uniform sampling, you have 2D measurements. But that is not what Gaia and Hipparcos sees. So one axis has much larger uncertainty. So we refer to this as a 1D measurement. Now, this is the complication that really threw me for a long time to actually understand, is that at every time you no longer have an RA and a deck. At every time, all you know is that the star lay somewhere along this uncertain axis. So in other words, you only know its projected position. So I've shown here the AC axis, the across scan, that's the uncertain axis. And this line, in principle, extends very far. So I've just shown a segment of it to make this less cluttered. But all you know is that the star at that time lay along that line. And you also notice here that these scan angles, so the angles that these lines make with the plot, are actually rotating, which is what real Gaia would actually do, what it actually sees. But anyway, so the fact that you have these 1D measurements can make fitting orbital motion kind of tricky and a little bit non-intuitive, at least at first. So I'm going to show a very over-exaggerated example. So don't think this applies to everything, but it's an exaggerated example of how this, in some cases, can be nuanced and tricky. You can have, in some cases, multiple solutions that fit the data nearly equally as well, but are very far apart in actual parameter space in terms of their orbits. So this is really non-intuitive to me for the following reason, is that when you're fitting 2D measurements, you have some best fitting model that runs through them. And you'd expect that the nearby solutions in likelihood space, the solutions that fit the model almost as well, are also nearby in parameter space. Let's say your best fit eccentricity is 0.7. You'd expect that, okay, maybe 0.75 and 0.70 or 0.68 or something also fit the data okay. But when you have 1D measurements, there can be cases where this is not true. Okay, so I'm gonna ask a question here. So I'm going to show a bunch of slides with trial orbits, and we're going to try to see if people can tease out which one of these are like these degenerate cases. So in white, we have, again, the best fit orbit with the data we're drawn from, has an eccentricity of 0.4 in a period of 3 years. And in gray is an orbit that's very different. So a 0.7 eccentricity in a period of 2 years. So this would be, a totally different orbital architecture, very different interpretation for the physical system. And what I want is people to give a thumbs up if they think that the gray orbit's going to be an okay fit, and a thumbs down if they think it's going to be a clearly worse fit, but maybe still, okay. So thumbs down for worse, thumbs up for okay. So I'm seeing almost universal thumbs down. In fact, both of these orbits are great fits and perfectly identical fits to these data. So just watch this movie carefully. I'll let it play a couple times. At every single time, both of these inferred sky paths have the exact same projected position. So they are both identical in chi-squared. Again, this is a contrived example, but it's just supposed to show you the nuances of working with 1D observations. And I'm glad to hear that reaction, because yeah, this is kind of crazy, right? It's like weird. Okay, so just remember that intuition that, this really takes some careful analysis. And it's one reason why this problem is hard. It's hard to develop intuition, and it's hard to develop confidence intervals on your fitted parameters in some cases. So in this, I showed you a contrived example of two very different orbits that can fit a single absolute astrometric path. So this is contrived, but in the hands-on session today, there's an optional notebook, which I think is really cool, where you will do the exact exercise. You will fit orbits to simulated Gaia observations with realistic uncertainties. They're simulated, but they're closer than my crazy example there. Yet, you will find that when you fit orbits, you can develop actually a family of solutions that are very different in orbital parameter space. So sort of like this example I showed, very different eccentricities, very different periods. And so this illustrates one of these problems where if you have two orbits that are really far apart, so your inferred parameter space is multimodal, how do you report a confidence interval in plus or minus sigma? E plus or minus 0.1. It can become difficult to say that, and difficult to report and difficult to understand. So it's a tricky problem. So the last complication, which I'll just touch on, is again, no data set is perfect. So when these positions come out, there could be negligible systematics meaning some additional signal on top of the true astrometric path. There could be systematics in the bright stars, there could be and none in the faint stars, it could be flipped. We don't know, and we don't know what might come out of this. And again, no data set is perfect, so there's no reason we should expect perfect. And again, it's a good thing, because if it's not perfect, then there's lots of work for everyone else to do, and lots of cool science is going to lie between kind of bringing the reality closer to perfect that you can do. So we have a discussion of this. I'll just plug my own paper that's coming out in the context of Hipparcos, not necessarily to point out anything wrong with Hipparcos, but to kind of give some intuition and some nuance of how we might tackle these problems in the context of Gaia. And it's more of a pedagogical understanding of systematics in these on-sky positions. So if you really like digging into the detailed statistics of Hipparcos, which I don't, maybe if you do, I don't know, but I really like it. But if you really like detailed statistics, this paper is just a lot on that, and kind of understanding this. Okay, so the two big takeaways that I want people to remember. So combine direct imaging with absolute astrometry, the on-sky positions can be really powerful. So I showed you that slide where you have two very different orbits, different eccentricities, different periods that are degenerate with each other. But what's one way to break that? Like two direct imaging points. So if you have some modest constraint on, the eccentricity or the period from another data source, or an eccentricity constraint from the RVs, then this becomes amazingly powerful. They both complement each other in this wonderful way, and you break this degeneracy and get an actual true companion mass. So this is incredibly powerful. And right now is like basically the golden age of open source software. So you dial back to like 4 or 5 years ago, and there are not many well-supported orbit fitting softwares that can incorporate all these different types of data. They were out there, in certain groups, and if I'm glossing over any that were open source and were out there, then I apologize. But when I was a new graduate student, it was hard to find those things. But right now we have a bunch of different software. So in addition to Orvara, there's others. There's also Orbitize, which as of this morning, when I checked the GitHub, there's an open pull request that looks like it's about to be merged that will actually implement the Hipparcos Gaia catalog of accelerations. So now there'll be 2 really actively developed code bases, at least, and again, apologies I'm glossing over anything, that can fit orbits from many different data types that can be compared against each other, that both have their own pros and cons. And so it really is the golden age of doing this. And the second big takeaway is just that, play with these 1D scans, try to get some intuition for them if you're new to them, because it can be tricky and it's a difficult problem to get right. And so thank you, and I'll take questions.
Okay, that was excellent. I'm sure that this very cool animation will teach even a lot of us in Deepak something about these degeneracies in fitting orbits. Okay, we have time for questions.
So we have one online question asking what raw Gaia data is htof downloading?
Right, that's a great question. So right now, we don't have the actual raw on-sky positions. What we do have is a set of predicted observation times and scan angles from Gaia. And those are not going to be perfect. There are going to be some that have been thrown out in the ground-based data processing. And there are ways we have in htof, that I don't want to get into details, of determining. We can never say that the scan angles from the ghost predictions are perfect, but we do have ways of saying that they're not. And so there are ways to kind of vet and tell, okay, is it okay for me to use the scan angles in this case, or is it not? Does that answer the question? Was this an online question? Okay.
Yeah, and if you really want to get into it, there are also calibrated versions of the scanning law in works by Douglas Boobert and Andy Averill. This is also available on GitHub. So those are slightly more accurate than the ghost, but for playing around with simulations, that's more than sufficient, I think. Yeah, go ahead.
Yeah, I have a question. Maybe it's just me not understanding it, but with the 1D positions along the scan direction, can you use the information of, let's say, other stars that are along this 1D scan to determine where the position of the stars should be? So it's a relative position once you get another star along the scan direction. So that's another constraint, or not really, because I don't know.
Yeah, so I think this gets down to the question of, okay, so when you treat these, you treat them as being the across scan error being infinitely long, but clearly it's not like a great circle in the sky. They have some constraint based off the satellite attitude of where these might be. And so I think in detail, I guess it's probably a better question for Anthony if you can do that. But my understanding is that the cross scan error is not infinite, but it's a factor of a few hundred worse than the long scan error. And so it's not really used. But I think tricks like that maybe are used. Okay. Okay.
I've certainly never thought about that, but yeah.
Okay.
So David, go ahead.
Hi, David Hobbs from Lund. I didn't understand this concept of the 1D versus the 2D scan. It's clear, of course, Gaia measurements are one-dimensional individually, but when you combine different scan directions, you effectively include two-dimensional information. And therefore, you can always fit an orbit to the two-dimensional information because the scans are from different directions. So I would say in the simulation you showed, the chi-squared, the minimized chi-squared of the first orbit would be much better than or much lower than the chi-squared of the other orbit.
Yeah. So you're. Oh, sorry. Go ahead.
Yeah. So I'm missing something here.
Yeah. So in short, you're exactly right. Is that the Gaia scanning law strives to not have scan patterns that are like this. So this is a contrived example. It strives to have scan patterns with many different scan angles at overlapping phases to get exactly what you're saying. So in this example, I can tell you that the chi-squareds are identical, but in a real example where you have, many different scan angles to break this contrived degeneracy, then yeah, I mean, in most cases, this is not going to apply. But in the hands-on session, you will see that this kind of problem can crop up with simulated scans in a sort of similar vein, but not as this. You're exactly right that it's not this bad.
Yeah, but I mean the CU4 are getting solutions for the orbits from the epoch astrometry, so there are other degeneracies, but you can still always fit an orbit with the chi-squared. What am I missing here?
Well, I mean, I think this is correct, even if contrived. And CU4, as far as I know, uses least squares, so that will just give you a single solution. And maybe if you do, a larger exploration of the space of possible solutions, you would find different possibilities. So this discrepancy that you showed in the actual case that you investigated might be one of those. I mean, I wouldn't be surprised if there are orbits for which you have more than one solution, given the uncertainties in the scanning configuration.
Yeah. Okay. Well, I'll
Yeah. No, anytime. Yeah. Thank you.
Hi, Merrick. Really great talk.
Thanks.
Cal Franson, UT Austin. So I was wondering what, if you have thoughts or a sense for which orbit elements are kind of most affected by the unique challenges posed by these 1D scans, and if there are other orbital elements that are significantly easier to pin down with this kind of epoch astrometry from the 1D scans.
Yeah, it's a great question. My short answer is no. I think it's going to depend on what the exact source is to figure out where biases might exist, or exactly what Anthony mentioned of doing an exploration of what does the likelihood space actually look like for these different orbital elements for the specific source fitted. But in general, doing absolute astrometric stuff gives you access to unlocking the inclination in that individual masses. Does that answer your question?
Oh yeah, thank you.
Yeah, thanks for the question.
Okay, are there any more online questions? Okay, good. Then let's thank